In this lab, we discovered the relationship between distance and magnetic fields derived from Biot-Savart's law using a bar magnet and a magnometer app on a smartphone. In order to most accurately measure the magnetic field, I had to first ensure the Earth's magnetic field was not impacting my results by rotating the magnometer until the x value was 0. Using this, I then calculated the distance at which the magnetic field was equal to 1,000 microteslas. The average of my three calculated values ended up being 0.071 meters from the magnet. Using this number, I calculated what the magnetic field would be at 1.5, 1.75, and 2 times that distance. Using this data, I was able to graph the result and find the slope by taking the natural log of both sides. The slope was -3.0784, which is useful in helping calculate the relationship between distance and the strength of that magnetic field. Using the equation magnitude of B bar equals KR raised to the N, you can calculate the magnetic field at distance R from the magnet. For a bar magnet, the theoretical value of N would be -3. Which means our value of -3.0784 is close to the actual value. In order to model the magnetic field in 3D, we use the formula B equals K times 1 over r to the third, in parentheses 3, in parentheses, mu times r hat, close parentheses, r hat minus mu, close parentheses, to calculate the distance at vector r. In order to use this equation, I had to find the value of mu to put into my code. To do this, I used my previously calculated values for the magnitude of the magnetic field at the distance where the magnetic field is equal to 1,000 microteslas, 1.5 that distance, 1.75 that distance, and 2 times that distance, and plugged it into the equation B dipole on the axis equals K times 2 mu divided by r to the third. And I got 4 different mu's. I then took the average of the 4 to get the value 1.71465. To create my code, I had to plug in all of the previously measured values, including my mu. I then had to create a function using mu and r that would return the magnetic field. I used the equation that I had previously talked about, calculated the dot product separately, and then plugged that into the equation and had it return the magnitude B. My B scale ended up being 0.1 in order to make the arrows fit onto the screen. For the arrow position at 45 degrees, I used the previously stated given for loops and multiplied that by the r hat value at a 45-degree angle, which would be 0.707, 0.7070 for the positive x, positive y direction. I then multiplied that by the negative x for the negative x, positive y direction, negative y for the negative y, positive x direction, and negative x and negative y for the negative x and positive y direction, which resulted in this model. As you can see, the yellow arrows are the arrows on the x-axis, the red arrows are the arrows on the y-axis, and the blue arrows are the arrows for the 45-degree or any other axis. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? If the experiment had not compensated for magnetic north, the distance needed to reach 1,000 microteslas would be slightly shorter because the x value would have an extra magnetic field adding onto the bar magnet's magnetic field. Since it would be a constant, however, the slope and resulting value for n should not change. What if you were to stick two identical magnets together, end to end, and run the experiment again? How would you expect your measurements to differ? The measurements would be almost twice the magnitude, but not exactly twice since the second magnet would be slightly farther away. To conclude, This lab helped model and better understand the magnetic field of a bar magnet and how to visualize the resulting field.